Thank you, Herman. Yeah, thank you, everyone. Today we are going to look at specification of a reference clock in the context of one clock that can be used to address most of the applications. This is mostly from the fact that the key application that we are looking when we look at the compute and the telecommunication coming together is 5G. And as you know, there is a major change in the front haul that is happening today where we have the O-RAN coming into picture that is splitting up the baseband unit and the radio into various components as we see today, the CUs, the DUs, and the RUs. So here, if you look at the various segments in terms of the radio, in terms of the RAN, in terms of the DU, transport, and the core network, the standard bodies who are involved in defining the requirements in each of these segments vary quite significantly. So there is significant overlap or significant, I say many people talk about what they need in their specific segments here. But most of them can come back to two standard bodies. One is the 3GPP and the second one is the ITU-T. So today's presentation is mostly focusing on what oscillator can we use so that the compute or the switching portion in a data center can address the telecom requirements of the world, basically the ITU-T part. So if you look at the NIC or DU server that can be used in a telecom environment, we can see that if this were to support a radio, then the radio needs to have these 5 ppb over 1 milliseconds requirement and the phase requirements of say 130 nanoseconds all the way to 1.5 depending on what kind of networks you need to support. So this is overall. We will see that in a later time. Secondly, what kind of network is driving the radio through this server that we are talking about? Is it using the traditional SYNC network, which is a G.8262 like networks? Then probably we are looking at maybe a 10 to 75 millihertz like loop bandwidth in the endpoint. But how much is that that is required in the switching or the compute element itself? Third is if you are looking at the G.8273, 73.2 like clocks, which is basically the TBC type and different class of clocks, then we are looking at 50 to 100 millihertz. Is there a GPS coming into the system? Then probably we are looking at about a 10 millihertz filtering in order to support the GPS. If you have partial timing that needs to be supported, then it goes into a 1 millihertz range of filtering mechanism. Those are on the synchronization. There may also be say phase noise requirements or jitter requirements that are required depending on the kind of interfaces that we use in terms of the services that we use. So if you look at the specific numbers to address, probably we can look at it from two perspectives. One is the network requirement. The network requirement is driven by this TSN, IEEE 802.1 CM like network requirements, which says that you need to have the end application requirement of these numbers depending on the type of services that we offer. So that's the at the end, from a reference point till the end, we need to have this kind of performances. And the network itself can have these numbers. The time error, time alignment error can be these. For example, if you have a GPS or a GNSS, you have a GNSS-based grandmaster, you have a switch and a radio, then you need to say, for example, supporting this level of service, we need to support 130 nanoseconds. So if you use a traditional GNSS machine, you may not be able to use it because the network only has 60 nanoseconds. So we have to select the GNSS accordingly and so on. Similarly, if you look at the transport, we have the various types of networks that are saying that you need to support this level of performance. And most important, you can see the dynamic error, the error only, that is error, intrinsic error from the system, and the maximum error that needs to be within those limits as we see here. Now, ITU-T, this is an overview of the ITU-T clocks that we are talking about. If you see here, these are the physical layer supported clocks. This portion is packet clocks or the protocol layer clocks with the full timing support. every network element supporting clocks, and this is a partial. Some clocks supporting, some elements supporting synchronization and some may not. And in a practical deployment scenario, the assisted or partial, assisted meaning GPS is your main clock, is supported by PTP and Synchy, but it is partial. Some elements may have synchronization, some may not have synchronization. So that's the key overview we need to have, and then from these we need to select. When we build an equipment, most likely considering that you need to support the mobile network, the requirement from 3GPP, we say, okay, what all boxes I need to tick from this? That's generally what we see today in most of the applications in the computing world or switching world that is going to work with the telecom world. So if you look at the impact of the oscillator, we were talking about the oscillator and what is the requirement of the oscillator. It's mainly, if you see, the generic block diagram of an oscillator of comparing the output phase. When the system comes up, whatever in the oscillator will be reflected on the output, and then the output gets compared with a nominal frequency that comes from the network, and then this phase comparator will drive the DCO to get this nominal at the output. So if you look at the specific values, we are looking at free run, wander. Wander is as in the intrinsic generation of the error, which is actually the high pass effect of the oscillator. If you think about it, if the loop bandwidth is very fast, the error on the oscillator and the output will be minimal because I'm always correcting. If the loop bandwidth is small, then as the oscillator moves around, Gary was mentioning about the sensitivity, the interval between corrections will have an impact on the output. So that's the wander generation part, how much error that gets generated within the oscillator if there is an environmental change. And then holdover is the idea of leaving or not having the clock, but still the system be able to sustain certain amount of accuracy. And finally, the jitter or the phase noise we talked about. So these are the impacts. And I wanted to put down the various types of clocks that we see. For example, if you look at the traditional clocks, these are 812, 813 type of clocks. These are no longer used much. These are from the SDH or SONET world. These, when became the synchronous Ethernet, most of the people took these, most of the specifications were adopted from this world into the Ethernet world. And as you see, depending on the specifications we described earlier about the free run part, the loop filter part, the frequency versus temperature, aging, we can see that we have some numbers to meet. And then accordingly, we can look at certain oscillator technologies based on the capability of the oscillator technology today. For example, if you are looking at, say, synchronous Ethernet, we are saying that the loop bandwidth needs to be in the range of 0.1 to 10 hertz. And in order to get a certain level of error, you need to have probably a TCXO or a hybrid TCXO level of technology which has these features. About 300 ppb stratum 3E level, stratum 3 level of frequency versus temperature, and maybe 10 ppb level of accuracy. So like that, you can see that the next version of the Ethernet equipment clock is a bit more relaxed, but the oscillator technology needs to be similar. If you look at the packet clocks, we have a packet equipment clock. This was the original packet clock that was designed based on the G.8263, and the master clock of that is G.8266. And if you see the G.8263, then it is requiring a 10 ppb frequency versus stability and aging of 1 ppb. So mostly an OCXO is required at this time in order to meet this level of accuracy. Similarly, as we move on, we have the full on-path support. This is the G.8273.2 type of clocks that is talking about the TBC and TTSC needing to have a certain level of stability. Transparent clocks need a certain level of stability. The assisted and partial timing support clocks, these are the G.8275.2 profile, and the supported clocks are G.8273.4 type clocks. They will need much more stringent level of stability because now some of the nodes are not supporting synchronization. So your packet delay variation is much more. Your our loop filtering or the averaging times are much stronger. So you need much stringent oscillator technology to support such clocks. So In general, I think if you think about the 3 slides that we had in terms of the traditional clocks, in terms of the packet clocks, and in terms of the latest on-path support and transparent and the assisted partial timing support clocks, this covers the basic requirements of clocks that needs to be supported on this telecom grade equipment, and that needs to come into the systems. But when we design a system, usually, and okay, taking a step back, you can see that some of these requirements need a lower level of stability clocks. Some of them need intermediate level, and some of them need higher level. So can we get into one oscillator specification that can meet all? Maybe yes, maybe not. But I'm trying to bring in one specification that can meet all the requirements to say that, to also say that when we design the equipment, we also have a number of deployment scenarios. So it needs to meet all of these scenarios. For example, from the entirely unaware network. Unaware means the intermediate nodes have no idea of what's happening. Only the master and the starting and the ending clock. I can't remember the latest terminology that we uses for these. Primary and secondary, and uses them, and then all the way down to the entire node. If you look at the fully aware network, from the master into the final node, everybody has the capability of physical layer timing and protocol layer timing. So in between, there are so many deployment cases. For example, if you look at the RFQs that we see from the carriers in the United States, they are looking at something like a partially aware no syncy support. So this is the type of network that we commonly see. So what kind of oscillator shall we use there? Or if you go to a fast growing network, then we can see, for example, some of the European networks, they have all syncy, but no PTP in there. I can't see where it is, but that's another option. So how do we select that clock? How do we design an equipment that can cater all this? So one possibility is to look at one oscillator that can do. And that's where, if you look at the Stratum 3E clock, that's an option. Stratum 3E talking about the temperature stability of 10 ppb peak to peak and the aging of 1 ppb per day, and then some stabilities. These are the potential capabilities that are available today. But it could also be an additional or one level better clock. These are also commercially available clocks that are economical to be used at 1 ppb per day, 1 ppb peak to peak temperature stability, aging of 0.2 ppb, frequency slop of say 0.01 ppb per degree Celsius, and some power stabilities and holdover capabilities and so on. So if you select a clock like this, a clock, there is nothing called Stratum 3E plus. I'm just saying it that it is the next level of Stratum 3E. Then you'll be able to support all these clock types. You have physical layer clock types, all of these what we just discussed. You can have the frequency type packet clocks. We can have the time-based packet clocks and the clocks that are required for base station as well as holdover. That's the presentation for today. Just to tell you that there are multiple standard bodies that are involved in the front hall, DU, and the radio part when we do look at, the combination of the compute and telecom communities together. And we could look at ITU-T and 3GPP in order to see that those standards are good enough now to have equipments compliant, and then look at these standards. And I am suggesting one of the oscillator specification that can be used to address all these possible compliance scenarios. Thank you.
Thank you, Ullas. So floor is open for questions. Any question? Okay, I have a question. So
Okay, please.
when it comes to PDV, like how do you relate that? Like I'm assuming like these oscillators, let's say you put them in transparent clocks. So how is that related, you think, like, or the effect of it?
Yes. So for transparent clocks in general, if you think about it, the PDB may not have an immediate impact. It is only the time between the ingress timestamp and the egress timestamp, how much the oscillator varies. So it's generally probably in the TCXO range, in the ppm range is what we are looking at. But the PDB is the key thing. That's the main thing. For example, if you think about how we address the PTP deployments, what we have is something called a filtering mechanism and selecting the lucky packets. So the lucky packet selection is the key part, that the averaging time gets extended. That's why we are talking about partial timing. We average much less than 1 millisecond. So PDV pushes the averaging in the servo to be much larger than 1,000 seconds. So in 1,000 seconds, depending on the oscillator that we use as a reference, something can happen at the output, because in that averaging time, everything belongs to the reference clock to manage the output. And can the output deviation in terms of frequency and phase be within the limits if the averaging time becomes bigger? That's the whole thing. You're absolutely right. PDV is the fundamental thing that determines the selection of the oscillator in the packet networks.
Any more questions? So another question, maybe like with all the specs you have for the oscillator, I mean, there's that much you can do. Let's say, I mean, you can't really improve the precision. So how are these specs that you're showing are, let's say, affecting like what you can get from a servo ultimately? I mean, there's always an upper bound you get to it, but not you don't necessarily get it. But then you really cannot go above that, you know, permissible limits. So how can we get that like from the specs so we know that anything beyond that is really not permissible?
Yes, I think this is also the key thing. With the new requirements today, somehow we need to translate that into what are the key parameters within the oscillator that relates to, or that limit, that gets to that output requirement or the target requirement. And I think Gary's team and all of us are doing working towards getting that, to decipher what exactly is in the oscillator that is driving that. And in a traditional or in a general mechanism, we can always assume that most of the oscillator, the key parameter of that drives the frequency stability is the change in temperature. So mostly if we work on parameters and technologies that can limit the impairment on the output frequency with temperature, that's where the advancement is going to happen. And we have number of, there are new device technologies, there are new crystal-based technologies there are new resonator technologies like MEMS that are coming up. There are new packaging mechanisms that is trying to address this. Even though the absolute stability is one thing, but how we can limit the sensitivity to the problem. So we are improving the technology to address these requirements.
Any more question? Nothing from the servo guys? Yeah. Please come to the microphone. Yeah. Shortest distance.
Very unbiased opinion. Basically, you mentioned about the categories of TCXOs and OCXOs based on certain parameters like DFE, and which translates to the frequency, slope, and temperature. I agree with you, is very important. And especially during a long averaging time, the frequency slope is going to have a big impact. But then I request the forum here actually to adopt not technology-specific names, because as you know, as you mentioned earlier, there are certain technologies that don't need to follow the urbanized XO approach. Actually, we should just call it a classifier which talks to these parameters more than saying that you need a TCXO or an OCXO to meet certain requirements. That was my comment.
That sounds to me a topic for OCP TAP, so we'll definitely, we know where to find you, so.
I agree with you.
Wonderful. Okay, so yeah, thank you.
Thank you.
Ullas.